Hi everyone. Once again, thank you for joining today. I'll just share my screen. Okay, so as the continuation of the discussions which we did yesterday, we'll continue today towards last 2 days. Actually, I was talking about regression, and first day actually I showed that how you can do a linear regressions using some mathematical formulations using your own code, and then using some scalar function. And second, actually I showed that okay, you can actually understand what kind of error propagates for those kind of fitting or those kind of analysis. And then actually I already showed that if you think about the statistical way of representing the whole mathematical analysis, how actually you're going to do that, and what kind of like results you're getting from that approach. So basically we talk about two different approach. One is mathematical, one is statistical. In statistical, we try to understand what are the correlation between the variables and how the covariance matrix can help us to get back the actual final solution, like in terms of solving some differential equation based on the parameters theta. So those already I have covered, and the first and second day IPython notebook contains all those like code which actually I showed in the classes. And so if I already shared those codes, so if you want, you can download them and you can run it. And if you face some problem, maybe tomorrow, just let me know, or you can like send me an email. I can check it. But hopefully they should work. Now what I'll do, I'll talk about another approach today. So last today I was talking about the frequency approach, because we are talking about different numbers. We are looking into some specific values, and based on that we are trying to solve that same problem, right? Now from we actually going to move from frequentist approach to a Bayesian approach, and we are going to look into the same problem considering distribution rather than considering some specific numbers or specific values in between the parameter space, right? So I'm going to explore the same problem, but in the context of Bayesian analysis. So today the main lecture will be on the Bayesian analysis, and I just want to know how many already know about the Bayesian. Like, have you tried Bayesian analysis? I hope that theoretically you already know, but did you try some code, or you tried some problem where actually applied some Bayesian analysis? Uh, I just want to know what is the scenario for that.
Not
Yeah.
really, sir. Not, sir.
Okay. Okay.
The Bayesian analysis.
Okay, so then it is a very crucial topic, and I'll then slowly go through so that like you can understand what exactly the theory part, and how we are going to use those analysis. Okay, so so as I said that yesterday also we generate some data, right? And I am just going to use the same data to give the same like the flavor how actually you're moving from frequentist approach to a Bayesian approach. Okay, so the first few slides of the first few like blocks actually is just a generation of data, so I'm not going to talk about that. But if you have any query, you can ask me again, right? So is it like visible?
Yes,
Right.
sir. Yes. Yes.
Okay. So the first 4 slides basically is talked about. So I can show it from the beginning. So start. Okay. So as I just generating some data, so that's why I need to, I'm just choosing 20 points, and I'm fixing some slope value and intercept value, and I'm generating some X and Y, which I already showed. And then I already said that like we can make that Y a little bit noisy, considering that in non-linear data, it's not a direct straight line, right? So we can generate some new data also, considering some noise, right? So this is a data part, and which is actually the part of the previous IPython notebook, which we described very details yesterday, right? So I hope this part is not required, and if you have any questions, just let me know. Now the point is how I'm going to estimate these parameters M and C, or that means the slope and the intercept, considering it as a Bayesian problem rather than considering it as a like a mathematical or statistical problem, right? Obviously Bayesian, so Bayesian inference or Bayesian analysis is actually coming from the concept of the probability, right? So you know, in probability there is a concept, Bayes theorem. I don't know how many are already aware of that, but normally there is a specific rule or there is a theorem which actually make a connection between probability of two different events. So if I just define here, So I'm not going to cover the probability part, but in general probability, there is a concept of joint probability and the condition probability, right? So condition probability is like that, like let's say you want to find out the probability of some specific event considering some a specific constraint, right? If I give an example that okay, like if we have a data of last 30 days, what kind of either it is a rainy day or it is a just a warm day. So you can actually make a condition that okay, it can be a warm or it can be a rainy day, and you just want to understand like if previously yesterday if it is a rainy, what is the probability that tomorrow it can be a rainy or a warm day, right? So this kind of conditions it can make based on two different events. So let's say I have two different events A and B. I can identify, or I can actually make a connection, or I can find a relation between A and B using this base rule. So the what actual base rule provide? The base rule provide that, like, let's say I have event A and B, and I is basically information about those events. So whenever I'm writing I, it is just universal representation, and this actually informing that whatever the problem you're solving, whatever the information you have regarding that model or that problem, that is defined by I. So so when I'm going to say that, okay, I need to calculate the condition probability, consider that, okay, I want to know what is the probability of A with respect to B and some information I, that can be written in terms of this. And that's directly coming from the conditional probability. So it is just mathematical relations. If you want, you can go and check the proof. But right now, I'm just assuming that this is already well known. So what it implies that conditional probability actually is depending on, it's basically written as, okay, that probability of A with respect to B is actually the ratio between probability of B and probability of the joint probability between A and B. So this part, this probability of A comma B with respect to I is just a joint probability or the common probability of the event A and B together, and this the probability of B itself. So when you're talking about conditional probability, we're actually talking about A with respect to B. So basically it can be the ratio between your common joint probability divided by your probability of the second event, right? Similarly, if I want to write the probability of B with respect to A, then I should write that probability of common probability, that probability of A comma B with respect to I divided by probability of A, right? So this is just a symmetry relation. So from this relation, you can directly get that, okay, I can get a joint probability, this P of A comma B with respect to I is nothing but just a multiplication of probability of A with respect to B into probability of B, right? So that means basically it's just a simple multiplication between the individual probability of the event B and what is the joint condition probability of A with respect to B, right? Similarly, you can also check the same thing with, as I said, that this is symmetric relation. So you can also make the same thing with considering that, okay, this probability of B can also be reverse way probability B with respect to A, right? So this probability A comma B can also be written in terms of this, and that is actually directly coming from this relation, where actually you're going to calculate what is the probability of B with respect to A. That is nothing but probability of A comma B divided by probability of A, right? And that is written here. Does it make sense?
Yes.
Fine, right? Okay. Now once you know this, you can actually plug in this relation directly here or here, and then basically you can come up that, okay, this is the relation you're getting finally, right? So earlier it was written like that, okay, the probability of A with respect to B is actually ratio between joint probability of or common probability between A and B and divided by probability of B, but that can also be replaced or can be written in terms of probability of B with respect to A and probability of A and divided by probability of B. So now you can see this, if you compare this expression, this expression, there's only difference is that you are actually replacing the joint probability by another condition probability, where actually your event B is depending on event A, right? So actually you are going to find the relation, or you're going to find what is the probability of A with respect to B, but you are replacing that in terms of what is the probability of B with respect to A, right? So in terms of this expression, basically you are writing a condition probability with another condition probability, right? And there actually you're also writing this probability of A and probability of B. So this is the base theorem, And here actually the important part is that how you're going to interpret this relation, right? So obviously it can be like in theory it's defined as like, oh, this is the posterior information or posterior probability, because you're going to calculate A with respect to B, and for that you need to know what is the probability of B with respect to A, right? So that means basically once, until unless you know this relation, you can't get back this relation, right? So that means this is like you can say it's independent event, or this is actually depending on this event, right? So you need to first need to know what should be the probability of B with respect to A, right? So that's why this is called the posterior event, and this is called the likelihood. So until unless you know the likelihood, you can't calculate the posterior distribution. So that is one thing. Second thing is that since this is just an independent probability, right? Independent probability of A, and this is also independent probability of B, right? So you can say this is basically the prior information about A, right? And that is actually, it's called the prior. And this actually you can't calculate directly until unless you have the information about P of B with A and P of probability of A with B. That's why it is called evidence. So it is these are the terminology normally people use. So whenever I'm going to talk about the Bayesian analysis, rather than I'm talking in terms of probability, I'll talk in terms of this notation, that the first one is the posterior, this one is likelihood, this one is prior, this one the evidence. Okay, so that means in Bayesian analysis, in Bayesian inference, posterior is actually proportion to your likelihood into prior. Does it make sense?
Yes.
Okay, so now like we can replace this Bayes theorem in terms of this expression, and this is our normal and like terminology when you're going to talk about the Bayesian inference. So if someone asks, okay, how to calculate posterior, then the answer should be, okay, first we need to calculate the prior and the likelihood separately, and if we multiply likelihood and the prior directly, then actually you get the posterior. Okay, so I just give an example here. Like let's say I'm just asking a simple question: what is the probability that there is a fire given that there is a smoke, right? So the A and B are here, can be fire and smoke. So you're going to find out what is the probability of fire with respect to smoke, right? So that should be written in terms of what should be the smoke with respect to fire, that is B with respect to A, into the probability of fire divided by probability of smoke, right? So until unless you know this information, sorry, until unless you don't know in this information, you can't get back what is the probability of fire to smoke, right? I don't know if that like how much it makes sense to you, but like let's say I just give us some example in a practical numbers, right? So right now I'm just talking in terms of simple probability, but let's say I'm just talking in terms of some numbers. Okay, so let's say I have some information. So I just took this information from online, so you can get this in like numbers from online itself. So let's say we are going to evaluate what is the possibility of cancer. So this is just a simple example that how to calculate the probability of cancer present and diagnostic test, right? So for that, what are the information required? That okay, you have these three separate information. One is sensitivity, the second is base rate, and third is specificity. So sensitivity means like how many people actually let's say X number of people actually have a cancer, and out of that, how many actually got tested positive, right? So like you are assuming that okay, it's, in the basics test, or maybe they have some symptoms which similar to cancer, but after actually going to do the diagnostic test, how many actually coming up as a really cancer patient, right? So you don't know either early symptoms equivalent to a cancer or some other disease, right? So that is the problem you're going to analyze, and for that you already know this is the normally pattern, that okay, if 100% people actually coming they have a symptoms of a cancer, but out of 100, 80%, 85% cases, it looks like they are actually have a cancer. So that means 85% it is actually giving a positive result, test result. Similarly, you are getting some base rate, that okay, out of that in general in the population, what is the normal ratio of a cancer, right? So that is obviously should be a very small range, so that's why it is just 0.02%, just an assumption. And then the specificity that if someone is coming doesn't have a cancer, but also get a negative test. I have some symptoms. It is not a symptom of cancer, and when I'm testing that, I'm also getting a negative results, right? So these are the three information I already have. Now the question which I need to answer that, okay, can you estimate what should be the rate of positive, like true positive rate of this cancer? So now what I can do, I can just assume that, okay, P of A is given, that is basically the base rate, because you are assuming that A is the chance of a cancer, and overall total population, this is the number which actually shows that this can be this much a percent of people can have a cancer, right? So this is our probability of A. And similarly, you are considering that, okay, if some people have a cancer, then what actually the sensitivity, like if there are some symptoms of a cancer, actually how many actually coming up as a true positive detected cancer. So that can be a P with like P of B given A or with respect to A, and that is given 0.85. And this is just like it is like those who don't have any cancer and they're coming as a negative. So it is basically P given not a cancer, and that is basically P like P of B given not A, that means not a cancer, and that is number is given, right? So using base rule, what you need to calculate, first this P of B, right? So P of B here you can calculate in this way, that, okay, it can be written P of B can be written as like P of B with respect to A into P of A plus P of B with not A, that means complement of P of B with A, and similarly complement of P of A, that is P not A. So if you have this information, you can calculate P of B, and that is required because in the denominator, if you remember, in the denominator, in the denominator, you need to calculate the P of B, right? So now from this information, you can calculate P of B. So you can directly calculate P of B here, right? And similarly, if you want to calculate what is the probability of A given B, then it should nothing but this is the divided by P of B, and you need to also know what is the P of A. That is, you already know from here, and you also need to calculate what is the P of B given A, right? And that is also given here. So all the two information already given. Only you need to calculate this information, and once you know this information from this relation, then you can get back what is the probability of A given B, right? And once you actually calculate that, then you will get some that 0.339%, right? So this is just a simple example where actually you can actually provide some numbers for likelihood for prior, right? But in real sense, any questions regarding that? No?
No, sir.
Okay, so right now for this simple example, what you are considering that, okay, likelihood has some specific value, prior has some specific value, right? And what you need to calculate, the evidence, and you, based on that evidence, you can get back your posterior value, right? And that is calculated here. But when you're going to talk about some model or some real data, you can't get directly one value, or you can't directly know what should be the value of a likelihood or some posterior, right? If you know what the very specific value, then it's just a frequentist way of doing the analysis rather than Bayesian ones, right? Bayesian ones implies that you need to assume that is coming from some distribution. So this P of B and P of A doesn't have very specific number, but it coming from some distribution, and that actually need to incorporate into your analysis, right? So the example which I showed, that is just to give a notion that how Bayesian analysis can work with simple example. But in real scenario, since you don't know very specific numbers, you need to assume some distribution, underlying distribution of a model, and based on that you need to solve. Okay, so now I'll talk about how we're going to use this relation for solving the same problem which we are discussing from last today, this linear regression. Okay, now when you're talking about model, right? So we know that, okay, for that data which we have generated, for that data, the linear regression can be a best fitted model, right? So now for our case, linear regression is our one of the model, and we are going to see that if that model is actually working properly or is providing very good answer or not, right? And that verification you can do based on this Bayesian analysis. So in terms of the same, like once you know this relation, you can also map the same relation for any problem, considering a new parameter that called data, right? Because now we're talking about the validation of that problem, and for that you need to incorporate some data. So right now, this is same way of writing the Bayesian analysis the way actually I did. In normally, when you see some Bayesian inference paper, they not write in this way, but they write in this way, because here they're talking about theta is basically the parameters, right? So for our case, theta is actually m and c, slope and the intercept. So you're going to estimate what should be the parameter theta with respect to some data and information, right? Does it make sense?
Yes.
Because for our case, we have what you like yesterday also I showed that when you actually make a mesh grid, right, near the actual value of theta, you see that your like for different theta, your results are the error actually propagates in a different way, right, in the space, and it's basically ellipse nearby the actual point. So that means basically for our case, or for this case, this estimation of parameter theta is actually the posterior. Right. So for a problem, you need to first decide what is the posterior you're going to solve, and what are the actually likelihood, and what is actually a prior, right? So for this example, estimation of theta, that means estimation of slope and the intercept, is actually a posterior, and that can be written in terms of that. Okay, I can calculate the posterior. That means I can estimate what should be M and C with respect to some given data, right? And that data already we have. And now that can be written that, okay, now I can say this is just a likelihood that implies that, okay, this data can be fitted with some specific value of theta, right? So let's say I put some value of m and c equals to, let's say, 2 and 1, right? And for that, if my data is providing a good answer, that can be information for me. So this is basically that, okay, what is the probability of that for a given theta, your data actually fitted well with that. Okay, so this is just a like a fitting of my model based on given theta, right? So right now, what model I'm assuming that our model is linear regression, right? So if for some value of theta, if linear regression is actually fitted very well, then actually I can say this is my the likelihood. Does it make sense?
Yes.
Okay, and obviously what you need to also know that what is the, like yesterday I said that what you need to fix the range, right, for the mesh grid, right? I just fix the range in between plus minus 2 of the actual value of m and c, right? So but for real scenario, how you know that what should be the value, right? So you should know that what kind of distribution from where actually you're getting the value of theta, right? So you need to underline, you need to know what kind of distribution it has. So maybe m or c coming from, let's say, in between any value in between minus 0.5 to 2.5, right? And when if you see the distribution of that solution, then basically you can assume that, okay, we don't know which one is giving a very good answer, so you can use uniform distribution in that range, right? So I can say that, look, underlying distribution for the yesterday's example is actually uniform, right? So it can be any point in between that range or that box, and that can be my distribution. So this can be a prior information about the theta space with respect to distribution, and it can be a uniform, it can be a Gaussian, it can vary, or you can choose any of your own your own intuition to decide what could be the distribution of that prior, right? Okay, does it make sense?
So the P of theta is the probability of the distribution, or
The probability of no, so the P of theta means the distribution.
Achha.
So like here the probability and distribution is the same thing, right? Because
Yes, sir.
okay, so because you're picking some point based on that probability. So like the point is that what distribution you can choose, right, for your theta.
Yes, sir.
So I can, like, you can start with, okay, you are assuming that, okay, maybe for this problem theta can be coming from some Gaussian distribution, right? But I can say, okay, no, I am thinking maybe it is coming from some uniform distribution, right? So it is on up to us, or it up to user, whatever the probability they want to choose for that that prior.
Yes.
Does it make sense? Now, as I said that for yesterday's example, since I actually fixed that box, that mesh grid, right, near the actual solution of MNC, and then those, if you make a fix a box near that MNC, the original solution of the MNC, and then obviously in that box, any value can be a probable value, right? Can give a correct answer. How you know previously which one is a better option, right? So in that sense, you can start with uniform distribution. Right. So normally, whenever you have no idea about that distribution of those like parameters, then actually you can start with uniform distribution. Right. Uniform distribution means that there is equal chance that any of the combination of theta in that from that box can be give a optimal solution.
So for yesterday's example, P of theta is just a measure of how likely are we to choose a given point in the rectangle.
Yes, yes. So if you remember, yeah, like there's two things. First is we fix the box, right?
Yeah.
That means we fix the boundaries of that parameter space, right? So in that parameter space, in the very beginning, like without see anything, without knowing how the error is propagating, you can say that okay, any of the combination of theta M and C can give a solution, right?
Yeah.
So then basically you are saying that all of the point has equal probability.
Yeah. Uniform.
Right. Yeah, so then it is a uniform, right? But once you said, like once you actually calculate the error propagates through that space, that visualization, that ellipse, right? Then actually you know that okay, if you make the center point as your original solution, then basically if you choose a Gaussian distribution of prior, right? Considering that as your center as your center of your Gaussian or the mean position of the Gaussian, right? Then it is better to choose a Gaussian distribution, right?
Yes.
But the point is how you know that, right? Beforehand, you don't know either it is a Gaussian distribution, like how errors propagate, is the Gaussian distribution or it's an uniform distribution. So, so initially you are starting with the uniform, right?
Right.
Yeah. So there is a two thing. Like if you have no idea about your parameter space, then better to use uniform in some range, right? Now if you let's say if you started with uniform and you get some results and you saw that okay, now it looks like it is a sort of Gaussian, then for the next time when you're going to do the analysis, you can start with the Gaussian.
Right.
Right. So in general problem, what happened that like I can give an example for astrophysics problem. Let's say when detecting some signals, we are assuming that okay, we don't know anything about those detections, so we assume that whatever the parameter we're going to estimate, they are coming from some uniform distribution, right?
Yes.
Now let's say I have 1,000 event detections, and for each detection we have a clear idea how actually these parameters actually are like varying over the parameter space, right? So then what I can do, I can choose that as my another prior information, and based on that I can make whatever the distribution I'm getting from that information. So those 1,000 events can provide me a good estimation of the prior, and that can I use for the further analysis for upcoming events.
Right.
Right. Okay. So this is crucial because in general, if you come up, if you start with some like uniform distribution or flat distribution, so then basically it will take longer time to reach to the original solution.
Yes.
Okay. So okay, so that doesn't make sense. I'll not talk about this evidence part right now, but you can just assume that this is actually calculation of posterior is actually is proportion to likelihood and prior, right?
Yes.
Okay. So anyone have any questions? No, right? No. Okay. So then there is another concept which is very important, that is called marginalization. So ideally when you're talking about p with respect to like p with respect like this theta with respect to d, right, it has basically two parameters right now for our case. Oh, sorry, it should be okay. So whereas yeah, sorry. Okay, so Ideally, it has two parameters, right? So if you want to calculate, if you need to multiply, basically you need to calculate in this way. So ideally you need to calculate the p of theta with respect to d. It implies basically you are calculating m and c with respect to d, right? Now you don't know what is the correlation between m and c, and therefore it is very difficult to do this marginalization over a 2D integration space, right? So therefore what we normally do, we actually consider that, okay, if you do a marginalization over c, marginalization over c means like you are assuming that, okay, m and c are independent, and then actually you can write the same expression you can write. So basically you are going to calculate what is the probability m, right? So like we are separating out that theta parameter in terms of m and c. Fine. So right now, since I'm assuming that, okay, estimating the m is much more important for me. So what I can do, I can marginalize the whole this p of theta with respect to d by p of m with respect to d. Consider that c is not that much important, so I can marginalize the whole expression with respect to c. So I can do the integration over c. Otherwise, like if you want to calculate the theta, this m and c together, you don't know what kind of relations m and c has, then basically it is very difficult to do a two-dimensional integrations. It can be a very complicated to find out the solution. So to actually to simplify that thing, what we do that, okay, we just decide for which parameter we want to estimate the values, and for that we can marginalize over the other parameters. So if I say that, okay, I am interested with m, so I can calculate p of m with respect to d by marginalizing over c, and that is the formula we can do. Does it make sense?
Yes.
Okay, so these are the basic thing is important. Now this is just a Bayesian inference. So I will just give that how you're going to set up a Bayesian inference whenever you have some model, and whenever you need to going to estimate some parameter theta. Right now, the question is how you're going to solve this problem, right? So to solve the problem, we need to choose some sampler. And like yesterday, I gave that example. I don't know either you actually realize or not that I made that boundary mesh grid and choose some different combination of theta, right, in that space to see how actually error is propagates. But that has a very specific I did that intentionally. Why? Because like normally what you can do, you can actually make a specific grid, and for each data point you can go and check what should the value there to get back a posterior. But that is not a good option, or that is not a good way of solving the problem, right? Because if you remember, along that ellipse there is a maximum less error, but apart from that there are space in the parameter space, there's some part of the parameters where the error is very high, right?
Yes.
And so if you let's say if you only like choosing some points over there, then obviously you're not getting back the actual solution, right? So that means it's very difficult to identify the location of the original solution in that space until unless you are actually moving throughout the space, right? So that only possible if you actually jump from one point to another. Better to start from some specific range. Let's say I don't know what should be my initial value, right? So I can start with some any initial value, and if I maybe I should describe that figure. So I need to check. I need to open that Google Colab. Yeah, maybe I don't know either this makes sense or not, but I probably it's the first time. So let me know if it is very difficult to understand. So I'll help you to break it up. So what I was talking about, that from this problem, right? For this problem, let's say this is my space, right? Parameter space, right? So for this problem, if I start, let's say I need to give some initial value of m and c to run the Bayesian inference. So if I start, let's say I just give some value near this corner, right? So obviously at this corner, whatever the combination of m and c you are going to use, that will not give the actual solution or the optimal solution, right? Because the optimal solution should be lying in this ellipse, right? Does it make sense?
Yes.
Right. Now the problem is that if you're not actually moving fast to this space, it might be possible that you are actually taking longer time to reach to this point, right?
Yes. Yes.
So then what happened that like it will take longer time to get a solution in terms of your Bayesian inference. right? So like moving in that space is actually an important part. How you're going to move this space, considering different combination of MNC, right? I can choose infinite number of combination in this part, right? By just taking some very small increment on MNC, and I can explore only that part, right? So it might be possible that I only like stuck to this part, I'm not able to reach this part, right? So this kind of problem can happen. So therefore, when you're going to solve this Bayesian inference, we are not actually like making a mesh grid, or we're not defining the box. What we do, we just give some initial value, and we use some sampler. So what sampler does, that basically it actually randomly moving into the space. So it's not like that, okay, first point, maybe you've given this point, the next time it can jump to there, or maybe there. So it actually moving that parameter space freely, one point to another point, such that it can actually explore the whole parameter space very quickly. Does it make sense?
Yes.
Okay, so if it makes sense, so then then basically when you're talking about the Bayesian inference, you can't choose a set of MNC as initial or your sample points, which actually not able to explore the whole parameter space. So you need to use some sampler which can explore the whole parameter space. Now you need to so there are different sampler available, but there is a sampler called nested sampling also there, that's more efficient. But right now we are going to focus on one specific sampler that is called MCMC. So that is basically Monte Carlo Markov chain. So this is very crucial sampler. Whenever you're going to solve some Bayesian inference, you need to use this sampler or another sampler that's called nested sampling to actually to get back those samples for which you're getting a good solution. So now the objective is that okay, from this space we need to identify which are the combination of MNC for which we can get a better solution. Okay, so obviously from this plot it makes sense that okay, if you actually take the sample points from here, right, from this ellipse, then only you're getting a better solution, right?
Yes.
So the samplers actually the task of a sampler to identify those set of points for which it actually provide a good solution. Okay,
right. Hey, Amit, I have a question. Sorry.
Sure. Yeah.
The previous picture.
Yeah.
So all we have to do to find this red dot in this parameter space, right?
Yeah. So exact, not possible to exact go to that dot, but nearby dot. That's
yeah, nearby.
So,
yeah.
Yeah.
Right. So you said that we will not go for mesh grid, and we will try to
no. Yeah.
We will try to divide.
Because time complexity will be very high if you go for a mesh grid, and you don't know how to discretize, right? So if you, let's say if you started at this point and you would just very small delta m or a delta c, right, then it will take a lot of time to reach to this part,
right? We do not know discretization in the curved space, but in the flat,
yes,
you can do, right?
You can do in the flat space, but normally since you need to get a smooth posterior, you need a lot of sample points, right?
Yes. Yeah.
And those sample points should be, if those sample points are coming from this this ellipse, which is very the 1 sigma of the error bar, then basically you get a more good estimation of the parameters in terms of the posterior, right? So therefore better to, like, let's say if you want 10,000 samples, right, and if you make a mesh grid, maybe out of the 10,000 5,000 may be giving a bad solution, right?
Right.
So better to use some sampler which actually always give that specific area where actual solution can lie.
Right. No, I'm just trying to think that that also depends upon the accuracy we demand. For example, if we are trying to fit a line and we are only bothered about accuracy up to the second place of decimal.
But the point is here, you don't know, right? When you're talking about the Bayesian, you don't know what is the actual solution, right? What you want some distribution.
Yes.
So for this problem, the error propagation or the posterior, whatever the solution you're expecting, right, should have a Gaussian distribution.
Right.
Right, because if it is if the actual solution in the mean of your if it is in the mean in the your Gaussian distribution, then your that variance of that Gaussian is is little bit small, and that is the distribution you're expecting for this problem. Right. So if you use some sample simple uniform data points to actually to do this distribution or to calculate the posterior, then it might possible that the whatever distribution you're getting, that is not exactly the Gaussian, or it can be a skewed one.
Right. One more simple question. So the idea is the task of the sampler is to reach to that point quickly.
Yes.
Right. So the sampler, are they mostly based on Monte Carlo kind of scheme? I mean,
normally there are different version of Monte Carlo is available, but the MCMC is one of the sampler, and there is another is nested sampling. These are the two main sampler people normally use. But for Monte Carlo Markov chain, there are different versions available. So so people use based on their own choice which one is better. So it can possible that for different problems, different versions or different model algorithm can provide a better results. Let's say for some problems, the Gibbs sampling can give a more clear picture as compared to this Metropolis testing, which I am talking today.
Methods are by unsupervised.
No, my question was, let's say I start from one of the corners, right, which is the farthest distance from the center point. So is there any way that I can keep on moving in a one unique direction and to reach that point? I mean, some kind of...
So that is basically the Bayesian approach, right? That you know that what is the likelihood value, right?
Right. Okay. Yeah, please. Okay.
Sir, can I ask a doubt?
Yeah, sure.
He said that sampling might give us slightly faster results because of the random nature. Are we making any assumptions? I mean, this might be an irrelevant question. Are we making any assumptions about the sensitivity of the squared deviation with respect to changes in the parameters?
Yeah, so that is basically the question is that okay, if you want, let's say if you there are two options right now, that okay, you can move from uniformly from one point to another and you can do a random jump, right? So both the options there. And the question is how you're going to choose, what should the next point, right?
Yeah.
So that criteria is actually based on your likelihood. So what you need to calculate, your likelihood value at any arbitrary point of that space, right? And when I'm saying that okay, you're going to calculate likelihood, that means basically what you're doing, you are actually fitting your model with that specific value of MC the MNC, right? So yesterday I already showed that okay, when actually I'm making that mesh grid and I'm taking different combination of MNC for each and MNC. Actually, I am solving the same problem. And I'm trying to find out what is the minimum deviation from the actual solution, right?
Yes.
So that criteria actually help you to understand which point is actually giving a better solution.
Yes.
Okay, so that is when actually you're talking about in terms of Bayesian analysis, you are actually going to define the likelihood based on that deviation thing, and then that actually you can see for this example, we know we are expecting what is our model. Our model is basically a linear model, right?
Yes.
So this M is basically the linear model, right? That is basically in terms of matrix, it's basically X into some W or theta, right? And what we are doing that for different combination of theta, basically we are going to solve this equation, right? So we know what is the y, yi, and if we choose some theta, let's say theta 0 in that space, then we can also get some yi predicted, right? At that specific theta 0,
Yes.
right? And then we can find out what is the error.
Yes.
Right? And based on that, we can decide okay, which one is giving a better option.
Yeah.
Yeah.
Right.
So
Aziz,
make sense, right?
Aziz had the question.
Yes.
Okay.
The Monte Carlo method is like basically an unsupervised type of sampling.
So here actually I don't know in which context you're talking about supervised, unsupervised. Supervised means basically you have a training and testing, right? And when you don't have a testing and training data separately, then it is unsupervised. So in that sense, it is unsupervised, right? But in terms of statistical approach, we are not actually using the term supervised, unsupervised here, because you're not solving a classic classification problem or regression problem, right? Because here you're not looking for some specific solution. We are looking for a distribution.
Yes, sir. Like for sampling only I was asking.
Yeah, so then that is unsupervised. Yeah.
Thank you, sir.
Okay, so now the point is you are drawing at you are calculating likelihood value at a, let's say at theta 0 and theta 1, right? Now how are you going to choose which one is the better option? So you can calculate the ratio between these 2 points, so the previous point and the current point, and find out what is the likelihood ratio of the likelihood. And if your current point is giving a better ratio, like a value, that means basically you're going to accept that point, right? So it is simple that let's say there's A is a person, B is a person. They're actually there are 2 points in that space, right? So they actually solve the same problem. B also solve the same problem. So whoever give you the good solution in terms of the nearby the actual solution, that solution we are going to accept. Okay, so that's the way you can actually move around the parameter space. Does it make sense? So
we are kind of feeding the results of the sample to do better sampling.
Yes. So basically it actually give you guarantee that let's say you started with this point, right?
Yes.
Now if you move, let's say you're moving towards this, right? Then obviously your error will be less, right? So next point, if it is in the here, so obviously then it will give better solution as compared to this one,
so,
right?
So it will,
and
yes, so it will guide us to a rather
yes,
better approximation when
yes,
we
yes,
take each and every
exactly,
point.
exactly. So yeah, so it might be possible that it is taking a time to reach to the actual area of solution, but eventually it actually converts to the solution point.
So, but what if the distribution is random? Like we have selected the error distribution as some Gaussian or as of uniform type, but
like the errors are between 0 to 1.
Oh.
That bar is the error is a normalization. That's why a Gaussian is possible.
So like yesterday I talked about that, right? When you're talking about multivariate system, whatever the error propagation you're getting, it should be a ellipse kind of distribution. That means Gaussian distribution. It might be the longer or smaller depending on your noise variation, but theoretically it can be a Gaussian.
yes.
So that is also true for likelihood. Whenever you don't know what kind of distribution you're going to choose for likelihood, you can directly choose likelihood as a Gaussian. So if you see, this expression is basically the Gaussian one in a multi-dimensional space where actually it is the e to the power y minus that mean, right? So this is exactly the Gaussian. Normally people choose Gaussian. So this will give us better options always.
Yes. Yeah, this looks like the first term in the exponential expansion.
Yes. Exactly. Actually, it is there because if I have written in log scale, that's why it is a 2 term, but it is basically in exponential, it's basically 1 by 2 pi sigma square divided then e to the power 2 y minus x means your model divided by sigma square.
Yeah.
So it is a Gaussian one.
Yeah.
Right. So for any problem, when you're going to design your likelihood, if you know if you don't have any understanding of that, you can actually design in this way.
Yes.
Okay, so now what I need the model, right? So that model M, so that's basically the linear here. Similarly, I need some log prior, right? So I'm just assuming here as a flat prior, that means a constant prior, that is basically 1 here. Okay, and that log likelihood which I already described here, so this is already defined, right? And then basically you need to calculate the posterior, log posterior, that is basically in log scale is basically addition of your theta prior and the prior of theta and the prior and the likelihood, right? So these are the thing you need to define.
Yes.
Fine. So once you define this, then you can actually run your MCMC sampler, right? So obviously you're not going to write our own code for MCMC. We have a very specific EMCC package where actually all the samplers are already available. So I'm just calling that EMCC package. So you can install it and you can import that EMCC, right? Now, when you're calling this MCMC package from EMCC, you need to give some parameters for running that MCMC sampler. So, whereas right now we are solving a 2D problem, so it is number of dimensions should be equal to 2, and you need to give number of workers, right? So, what happens that normally it's actually required. It is not required for our problem, but it is required whenever you're going to solve a let's say 8-dimensional space, right? Like if you have a very large dimensional space, right? if you start only with one combination, might be possible that it will take longer time to like reach. So what normally people do, that they define number of different workers. So the workers actually working through that space and try to find out those samples for which it giving a better answer. So each and every worker is actually doing the same thing, and after individual workers actually getting some answer, whatever the workers actually providing the best answer, that we are going to choose as to decide the number of samples. So just like you parallelly you're running the same, you're giving the same task to all students, and they are solving. And whenever they are solving the problem, whoever gave that best solution, that you're going to assume as the best one. So workers are actually doing the same thing. So right now we are assuming that number of workers is equal to 50, and this burn in number of burn is actually that initially it might be possible that you are actually like deviating too much from your actual solution. So what you need normally do, that okay, you need to give us some like a lag period. So let's say if you're running for number of steps 3000, so you're assuming that the first 2000 whatever results you're getting, that is not good. So you're going to only choose after rest of the solution, that means the rest of 1000 as your solution. Okay, so and the number of steps means each worker is actually moving towards space 300 times. Basically it is actually considering each worker is actually taking 3000 sample points to explore the space. Fine, does it make sense? Okay.
Sir, so in each step that has been taken, so it gives us to a more accurate answer, or
yeah, you can choose more
less accurate one.
So number of steps required, basically, like obviously for a complicated problem, you need to give more number of steps, because you need more sample points near the original solution, right? To get a smooth curve. But for this example, it might not be required. Okay.
No, maybe.
So and yeah.
Sorry, maybe he is checking that if in the likelihood there are, let's say, more than 2 peaks, primary and secondary. So what are the chances that we are moving towards secondary, not towards primary?
Then you need to give a more number of steps to see the pattern of model kind of distribution, right? So it might be possible that if you give the less number of steps, or that means less number of samples, then it always like stick to one of the modes.
Yeah.
Right. So then you need to run for a longer period with more number of sample points.
Right. Yes. Thank you.
Yeah, and your number of n1 should be less than equal to your number of steps. It's expected, right? So okay, so this is the way you can define the initial guesses, and you can see right now this is a distribution of your initial guess. Basically is like for 50 workers, right? Right now I have a 50 workers, so individual workers required some starting point, right? So that is the initial guess of MNC for individual workers. Does it make sense? So yes. You can see for individual, all the workers, actually I gave like it took a random number in between 0 to 1, which is not actually near the solution, because the solution is around 1.5 and 2.5, right?
Yes.
Okay. Now you can run the sampler using MCMC. Sorry. So yeah, so now it's run, it is finished, because we have very simple like likelihood expression. But in some problem, if the likelihood expression is very complicated, or it's like it has a very long array in terms of vector, then basically it will take longer time to sample the whole space. So in actual problem, it will take almost 30 days also. Like in normally, as Sir knows that, like in our domain, when you're running this Bayesian inference, it actually take almost 30 days to reach to a good set of sample points. Okay, but for this problem, it is very trivial. That's why it is not taking that much time. And I just plotted those sample points. This is the final sample points after burning those discarding the first 2000 sample points, and then this I can say this looks like this exactly the same location, right, at where actually the best sample points are available, right? So these are the sample points, and then I need to visualize the posterior distribution, right? So for to visualize the posterior distribution, there is a specific package called corner. It actually generates some corner plot where actually you can see what kind of distribution you're getting. So if you import that corner, and if you just plot the posterior distribution, then you can see, right? Since I just use a noisy data, so then obviously I can't expect exactly the original solution at the center, but it can give you the very, very good distribution, right? Of if you, so this blue line actually shows the actual solution, that is 2.5 and 1.5, right? But whatever the estimation of your ellipse, right, and the corresponding distribution of your posterior for this intercept in the this slope is actually a Gaussian one, right? And that actually I already showed yesterday, right? That the if you choose some noisy data, obviously it will also show the same Gaussian distribution, but may be possible that your the direction of the ellipse is not exactly same as the original one, right? So does it make sense?
Yes, sir.
Yeah, but the point is here it's clearly found that okay, the peak is around 2.5, and that means it's actually giving a good estimation of your slope, right? But for intercept, it's actually little diverting from the actual peak because it has some noise part, right? So these are the solution got, and if you just calculate what is the solution you're getting, then basically you're getting the solution 1.5 and 2.44. Basically, these are the peak for the peak of this distribution. Okay,
So,
and yeah.
so if we increase the number of steps and the burnout steps, so will it lead to the exact value?
No, like as I said, that this data is actually let's say, I think it was a little misunderstood, but since what yesterday also I already showed, right, that this data is actually not in a straight line, right? So you are not whatever fitting you're doing, you're not getting a solution of 1.5 and 2.5, right?
Yes, sir.
So, but if I just replace, let's say I just replace the data here. So if I replace the data with the original straight line, so for noisy data, you can't get an exact same solution, right? Even in the frequency approach also, right?
Yes,
so you can get nearby 2.5. Right now you can say you can get exactly the same solution because it is actually the same exact thing, right? So now you can see this is very, very accurate because it doesn't have noise, right? So, but in practical, it has some noise. That's why you're not exactly getting that solution in terms of current exact value to generate the data. Does it make sense?
yes.
Okay, but here actually what is the important part? Important part that we are actually looking for distribution rather than a specific value, right? And now how I got this value? Basically, actually I just check the mean of peak of that distribution, and then basically I'm getting the solution, right? And that is actually basically like I don't know either you know or not. Like if you maximize over the likelihood, that will actually give this term called maximum of posteriori. That is called MAP, and that actually gives the best solution. So if you just take the mean of this two distribution, that is basically a map for this likelihood case, and this is the solution you're getting. Okay, so you can extend this whole analysis to any dimension for your own choice. So does it make sense?
Yes.
Okay, so any questions regarding this?
Yes, I have one.
Yeah, sure.
So you showed that we cannot measure, we can never measure the true parameters. Right?
Not exactly. Not exactly.
If the noise is present, right?
Yes.
So the role of noise will be to displace the parameters, true. So mean value will be displaced, but the width of the distribution should also change, isn't it?
Yes. Yes.
Sigma value should also change.
Yes.
Yeah, visually that was not what.
No. But the point is, like, if you assume that okay, we're expecting some Gaussian distribution, right? So you're getting a Gaussian distribution. Might be the possible that your peak is little bit slighted different from original peak, right?
Right.
But the distribution is not changing.
Yeah. Okay.
Right. So it is not like that due to noise you are getting some uniform distribution, right?
Yeah.
Right. And second thing, since it is marginalized over intercept, that's why for intercept you're getting a little bit slight different value. But you can see the estimation of your mass, M is very, very accurate, right? So if you see that the peak of this was 1.503 and actual is 1.5. So this difference for this M is very, very less. So it is accurately calculated, even if it is a noisy data. And for this, actually, it is getting a 2.44. Actual is going given 2.5, right? And that is manageable or like acceptable.
That is fine. I'm talking about the standard deviation of the two distribution. Will that also change?
Like a deviation from what? You don't know the actual
from the mean value. From the mean value we are getting. Let's say if we get 2.44. So the peak should be at 2.44, isn't it?
Yes. Like for this solution, obviously the peak should be at 2.44. Like ideally, I should give the value of these two here, right? But I just gave the actual solution, and I just showed that it is like slightly changed with the actual solution.
Yeah, got it. So this is the original value.
Actually. Yeah.
Thank you.
Okay. So actually, I want to also discuss one more thing. Okay. So you can just visualize this solution. That is not a problem. So I want to talk about how to present pipeline using sklearn, but maybe it's not possible today. So tomorrow I am going to talk about that part. But is it clear? Is somehow it is clear that how to actually operate or use this Bayesian analysis to same problem the way we were looking into last 2 days? Does it make sense, or it is a little bit improved from your previous understanding? Yes. I don't know like what is the feedback, but this is a very, very crucial topic, and I don't know like probably in all the workshop it is not always like covered. So I thought it is the one of the topic which people should know. And yeah, I just, if any questions, I already over the time, but I'll take 2 minutes if there is any questions. Otherwise, it's fine.
Right. So are there any questions from people online? Okay.
So for your own problem, you can design your own Bayesian analysis or Bayesian inference, and you can run this kind of solution. So the way actually I gave the solution for the straight line, that is actually already, if you go through this EMCC package, there is already, it is not exactly same the way actually I did, but almost they are similar understanding the way actually I was talking last 2 days. So you can go through this EMCC package, you'll get a more clear idea what exactly is going on. So that is basically exactly similar kind of understanding the way actually I showed last 2 days.